Hello, my name is Chad Green. I'm a scientist at NASA's Jet Propulsion Laboratory, and this video is all about how to use the MATLAB tools that I've written for It's Live version 2 Velocity Mosaic data products. Boom. All right, so the first thing to do is to go to my GitHub repository. That's what we're seeing here, github/chadagreen/its_live. That'll take you to the main page of the repo, which starts out with something like this. This map here is going to be useful for understanding what we're talking about. So just to orient ourselves a little bit, these black little squares all around the world are wherever we see glaciated regions. And that's where there are It's Live level 2 data products available. Level 2 meaning image paired data, the direct measurements. The colored squares over top of them are where we have It's Live level 3 velocity mosaics. And really the focus of this talk is on the level 3 velocity mosaics and how we can work with those mosaics in MATLAB. So the very first thing to do is to look for this repository and then get the data or get the code onto your computer. So there are a number of different ways to do that depending on how you interact with GitHub. I'll trust that you can get the repo onto your local machine and put it somewhere that MATLAB can find it. So for that, sometimes I use a startup.im file, which tells MATLAB to look in a certain path for code. I do that for my code, I do it for my data, and if you're unfamiliar with it, click on this link to the startup.im, which explains it on the MathWorks website. Once you've got the code installed on your computer and where MATLAB can find it, then it's time to get the data. There are 3 different ways to do that, and I've listed them here. And I'll go through them one at a time. First is with the NSIDC It's Live app. We'll start this in a new tab. So what we're looking at here is the It's Live NSIDC app. And in this, you can click on any region in the world and find the mosaics for that region. So if you want to do this manually, you can do this and then click on the netcdf file to download for Iceland, for example. And you'll notice that in this blue button, we have composite 120 meter. That's the resolution. Composite meaning this is the average velocity taken over about a 10-year period starting in 2014. And if you don't want the composite, you can go to a specific year going all the way back to 1985 if you so choose. So that's how you can get the data, just downloading it directly from NSIDC. Alternatively, you can explore the data on AWS. We'll check that out, what it looks like here. So on AWS, you can see it's just a regular file explorer. Click on Velocity Mosaic, version 2, and then choose whether you want the annual or static. And here static refers to the climatology or the summary mosaics, which are the default. Third and final way to get the It's Live velocity mosaic data onto your computer, if you don't already have it, is with this It's Live mosaic downloader function that is included in this repo. The way to work with this function is just to call the function name with a region number. So here, for example, region 5 is Greenland. So if you want to get the mosaic, the summary mosaic for Greenland, just call It's Live Mosaic Downloader for region 5. And once again, if you ever are not sure which region is which, just go to this It's Live Regions function, which will immediately just pull up this map to remind you. So again, we were just looking at Greenland, which is RGI 05A. And for these functions, we just refer to that as region 5. So in the It's Live Mosaic Downloader, by default, it only downloads the summary mosaic. But if you have a specific year and you want to download the annual mosaics, you could say It's Live Mosaic Downloader for region 5, and then specify whichever years you want to download the data for. Now keep in mind, these are pretty big files, so it does take some time to download several of them. Now back to the main page. So we've just covered what the It's Live Mosaic Downloader does and what the It's Live Regions does. And again, It's Live Regions just pulls up that map. as a reference. And now we can get into how to actually start working with the data. So you'll see that there are these two functions, itslive to geo and geo to itslive. These are transformation functions to transform coordinates. And these do require MATLAB's mapping toolbox, and it's just a convenient way to do the mapping transformation based on region number rather than having to remember which mapping EPSG code is associated with each region. So for example, if you have X and Y coordinates in meters for a given map projection, well, depending on which region, for which itslive region it is, you can just enter that region number. So 5 would be Greenland, and then you can transform these meters into geo coordinates lat long. Likewise, you can transfer them back into meters just with its sister function. So we have these two functions that work together and undo each other. Okay, so that's just how to work with coordinates. But getting the data into your computer or into MATLAB once it's on your computer is easily going to be done with this itslive data function. And I'll show you what that looks like. So itslive data requires two inputs, the region number, and then whichever variable that you want to pull in. Variable, usually you want the velocity, but you might want something else like the data count or the seasonal amplitude or something else. So here, for example, we're pulling up region 6, which corresponds to Iceland. And so we say itslive underscore data for region 6, and we say we want the velocity. And this gives us a velocity 2D grid and X and Y in these 1D arrays. Then we can plot that with image SC or pcolor and create this map of velocity for Iceland. Similarly, sometimes, we started with the Iceland because that's kind of a small region, and that's not really much data to download or to load into your computer. But for some of the bigger regions, especially like Antarctica, which is it's a very large mosaic, you don't always want to load in more data than you really need. So there is this extra functionality, which is optional for itslive data, which is you can enter the limits of latitude and longitude, or X and Y, and it'll only load the data within those limits. So for example, here I'm using an itslive or a basin data function from elsewhere in my GitHub repository. And this is just loading the outline of the Pine Island Glacier Basin in Antarctica, and just loading the geo-coordinates of it. That outline is this black line that we're going to see plotted down here. Now, if you only want to load the itslive velocity data that corresponds to this black outline, or just the region of it, then you say, okay, load the itslive underscore data for region 19, that's Antarctica. We say we want the velocity, v, and then these are the lat limits and lon limits, which correspond to these coordinates of the outline of this basin. So here we've only loaded the data, the itslive data that we see in this figure below. It's much faster than loading the entire continent worth of data. Similarly, you can, if you don't want the mosaic, the overall summary mosaic, perhaps you only want an annual mosaic for a specified year, you can do the same thing, but specify which year you want. Here we're saying the year is 2019. And then I've also added a buffer of 25 kilometers around each side. And this is what you see here. So we have entered the lat lim and lon lim corresponding to this black outline of the Pine Island Glacier Basin. And we say, well, we want just that much data plus an extra 25 kilometers on all sides. And that's what we've seen here. Now let's consider a time series. So the itslive data function loads in 2D data, so a grid of data for the mosaics. But what if you want multiple years so you can build a time series? For this, I'm going to use 4 spots along the Malaspina Glacier, And I'm using this because this Malaspina Glacier is a common example that we use with the ItsLive tools. And actually, let's check out this ItsLive widget so we can explore and see what we're looking at. All right, so here we've clicked on that ItsLive widget, and we have these 4 spots along Malaspina Glacier in Alaska. And down at the bottom, we have a time series of velocity for Malaspina Glacier. And you can move these little points around, by the way, and it takes a second to upload, or to update. But anywhere you move them around, you can explore how velocity has evolved over time. But you'll notice that this does have a bit of a seasonality to it. That's because it's including days, intervals that are less than 365 days. So we really see these seasonal ups and downs in velocity. But if we increase the interval between image pairs and actually make it only very long, well then, in this case, we lose that seasonal variability. And we only get these multi-annual signals. So depending on what you're doing, you can explore this ItsLive widget and find out what is going on in terms of time series. And this is really good for context. And I use this online tool in conjunction with the MATLAB tools very frequently. So here we're starting out with those 4 lat-long locations right along the Malaspina Glacier. And we're saying, okay, well, we want to develop a time series for the year 2014 to 2022. And just to exercise the usage of these functions that we've talked about, we say, okay, let's transform these coordinates, lat and long, into x and y. And then say, okay, well, we want all of the ItsLive data for region 1, that's Alaska. We want the velocity, and we want it for these lat limits and long limits with an extra 35 kilometers around each side. So 35 kilometers on each side of all of the 4 points that we're interested in. And we want it for these years, 2014 to 2022. Now we can load this data, plot the first year, and here I'm adding a few extra functions like the plot base map, which is optional but is helpful for context. And first, what you might see is this is Malaspina Glacier, which is the glacier we were just looking at. Here it's twisted around because the native projection for ItsLive is the North Polar Stereographic projection that is standard for Greenland. But for Alaska, we plotted in the same projection, which flips it around quite a bit. But that's because a lot of this data that we're starting with starts in the polar stereographic projection, so we keep it that way. And then you can create a GIF very easily, just updating that image we just created with the velocity data for each year. Now, moving on. Okay, so we've just covered ItsLive data. Now ItsLive interps. This is for if you want to interpolate velocity or any other field at a specified location. Let's check out what that looks like. So ItsLive interp works a lot like ItsLive data, except for you also have to enter the specific points of interest for interpolation. So for example, if you want to get the velocity time series at a single spot, here we're saying 2014 to 2022, and region 19, that's Antarctica, we say we want the velocity, and here are the geo-coordinates, and we want it for these years. Let's also get the velocity error. With this, we can plot an error bar as a function of year, so velocity and velocity error, and this is what we have for Bird Glacier, the velocity and its error annually. Similarly, here back again at Malaspina Glacier, using those same 4 points, just for reference, we say, okay, well, get the velocity at Malaspina Glacier. So here we're calling ItsLive interp for region 1, that's Alaska. We're calling velocity, and we want it at these lat long locations. And then here, for no good reason, I have plotted it as a bar, but here is velocity as a function of data point number. We can do the same thing. So I just showed that you can interpolate the velocity at a given location. You can also interpolate the velocity error, or for example, the count, the total number of image pairs contributing to a velocity estimate at a given location. And here, what we're seeing is a plot of error, velocity error, as a function of data count. This is just an exploration. You see that, first of all, the velocity errors are quite low, on the order of 1 to 2 meters per year. This one even rounds to 0. What you'll see is that the data error, it gets smaller and smaller the more and more data we include. And here it has gotten so small that it has rounded to 0. And the data error is stored within its live data mosaics as an integer value. So it's always going to be 0, 1, 2, 3, and so forth. You do see a little bump here, a little bit above 2. That's likely because this is linearly interpolated value on a 2D grid. So maybe there was one grid cell that had slightly higher data really close by. And moving on, just the same ideas. Let's interpolate the velocity for region 1 at 4 different lat-long locations and at multiple different years. And then you can plot it very easily, just as we've done before. It's not just single points. You can also create a grid. So here, for example, I've created a 50-meter resolution grid using mesh grid. And then interpolate the dv dt, the change in velocity per year, and also getting a 2D land ice mask. So here we plot the change in velocity per year and set all of anything that's not land ice, just make it transparent. And this is what we see. We see this acceleration of Petermann Glacier of a few meters per year from 2014 to 2022. We also have the ability to calculate flux across a gate. So in the previous example, using its live data, we called a function that gets the outline of the Pine Island Glacier Basin in Antarctica. That's this white line here. And suppose we want to calculate the total discharge into or out of a control volume like this. Well, there is a functionality to do that within this function suite. So I'll show you walk you through what we're doing here. First, we load in the basin data. And again, that's from a function that you can get here from my Antarctic boundaries function on GitHub. Then just look at the finite data, just get rid of all the nans and densify it to an even 100-meter spacing. Now, say that you want to calculate the velocity across that line, so orthogonal to the line, using its live interp for region 19, Antarctica. You just want the velocity across lat and long. And also for a flux gate, you would also need the ice thickness. So very similarly, I'm using my bed machine tools in a similar fashion. So interpolate the thickness along these same locations for Antarctica. And then the flux is the velocity times the thickness, flux per unit length. And so that's what we see here. We see this scatter plot where these little white dots are, white means that there's really no flux, and that's what would be expected all along this ice divide where ice velocity is 0. We don't expect, we don't expect any ice velocity to be crossing this flux gate all along the ice divide. We do expect it to be leaving this control volume right here at Pine Island Glacier, and that's exactly what we're seeing, these red dots saying, yes, the flux is flowing out of this control volume. So here, I'm using that same path distance along the line around the basin. We say, okay, let's plot the velocity across this line as a function of distance. And yeah, we see that the velocity is leaving the control volume in one little spot, and that corresponds to the main trunk of Pine Island Glacier. We also have the thickness from bed machine, and you can use that to calculate the flux across the line. Sum it all up for a measure of total ice discharge. This is what we see. We see the sum of the flow times dx. And what we get is about a 136.7 gigatons per year flow out of the Pine Island Glacier Basin. And that's on par with other measurements. It's about exactly what we would expect. And that is the total discharge. And the question is how much SMB, how much mass has come in through snowfall to balance that out. Okay, so now let's look at itslive image SC. This is just a plotting function to make it very easy to make plots. So for example, if you just call itslive image SC for region 5, it plots the entire velocity for region 5, which is Greenland. Now, I will say that it helps to call itslive image SC after you've set the extents of a map, because it's only going to load enough data to fill the extents of a map. If you call it for an empty map, like we did with Greenland, then it'll load the entire mosaic. But here, what I'm doing for Antarctica is I start a map, then say zoom to Pine Island Glacier first, make a MODIS mosaic of Antarctica low contrast map, and then plot itslive image SC for region 19, plot the velocity, and set the transparency, the alpha value, to 0.8, so it's a little bit semi-transparent. And this is what we get. We get this map of Pine Island Glacier overlaid on top of the MODIS mosaic of Antarctica. Moving on, very similarly, itslive quiver is just an arrow plot, and it works very much the same way as itslive image SC. So similarly, you want to zoom to your location of interest before calling this if you can, just to reduce the amount of data that's loaded and plotted. And so zoom to, for example, these axis limits, which I happen to know correspond to Jakobshavn Glacier in Greenland. And then say itslive quiver for region 5, that's Greenland. And then also plot a base map. This is optional. This is what we get. We get these quiver arrows showing the flow of the Jakobshavn Glacier. You can also do the same thing and format the arrows. For example, here we're showing thick red arrows, doing the same thing. And you can also specify the density. So the default density is 75, but here we're specifying 150 as the density. So there's more arrows and they're a little bit smaller. If you like the high density of the arrows, but you want them to be longer, then you can then adjust after plotting. So the auto scale factor, for example, makes them longer. You can change the color to black, and that's what you would get here. And finally, itslive flow line. So this function calculates flow lines along a glacier path from a single seed location or multiple seed locations. The way that works is the syntax is just to specify the region, as we typically do, and then seed locations for the flow line. And this will calculate the flow line downstream, but also upstream of that seed location. So for example, this glacier in British Columbia, we're going to have the seed location xi, yi. And let's take a look at it. So here I'm creating a new figure, setting the axis limits to around this glacier that I already happen to know, and then calling itslive image SC for region 2. That again is just plotting the velocity data for region 2 within these axis limits. Set the color limits from 0 to 200 meters per year, and plot the location of the seed location xi, yi as a yellow pentagram, a yellow star, with a yellow face. And add a base map if you want, and make the color map red. This is what we get. We get this beautiful network of glaciers in the mountains, and we have this yellow star indicating our seed location for this flow line. Now, from this seed location, you can calculate the full flow path by saying itslive_flowline for region 2 from the seed location xi, yi. Now, add this as a thick yellow line. Once you've calculated it, this is what we see. We see this yellow line overlaid on this glacier, and you see that it goes upstream and downstream of that starting point. Similarly, you can do it for multiple different locations. So here I've created a 20 kilometer resolution grid. You can see 20 E3 of these points in northern Greenland, right along Humboldt Glacier here. And let's calculate seed locations, or calculate flow lines from all of these locations. And what we get is these black lines, and you can see there's a line that passes through each one of these seed points. Now, to dig in a little bit more, let's do an example from Pine Island Glacier in Antarctica. Here we're calling it X seed and Y seed as the locations in meters, easting and northing. And just as we did before, let's create a map, zoom it to Pine Island Glacier, make it about 200 kilometers wide, and underlay low contrast mosaic of Antarctica image. Then add color, itslive image SC, as a semi-transparent, that's 0.75, semi-transparent color map, and set the color axis limits, and plot this seed location as a white circle with a red face. That's what we see here, white circle with a red face. Now, we can calculate a flow line from this seed location, and this time we're going to not just get the x and y coordinates of the flow line, but also get the distance along that flow line and velocity along that flow line. And here I'm plotting the flow line x and y first as a thick white line and then as a slightly thinner red line, so we get this outlined line effect. This is what we see here. We see this red line passing through that seed location and going off the page. So let's zoom out a little bit to see this whole flow line. And you'll see that it goes way up here to the uppermost part where it drops below, until the velocity drops to below about 10 meters per year. Now, what we can do is plot the velocity along that profile in terms of distance, because when we called itslive_flowline, we had this d variable return the distance in meters. Here, we divide by that distance by 1,000 to plot it as distance in kilometers, and then plot the velocity as a function of distance in kilometers. This is what we get. This whole area, 500, 400, 300 kilometers upstream of that seed location. Velocity is very low, but as the glacier approaches the coast, velocity increases rapidly. And just for a little bit of context, the lower panel, you can see how to plot a bed machine profile. And what we see is that seed location 0, the point along is the distance. It corresponds to the grounding line, and beyond the grounding line, the velocity is quite steady and high. So that pretty much sums it up. And if you have any questions about how to use these functions, or if there's a particular functionality that you would like to see, please feel free to reach out to me personally or raise an issue on GitHub. And thank you for watching.